Let's get back to robustness. I keep destroying things. Okay, shouldn't have done that. There isn't too much to add here. Just a few sections, and so this was the end that we got to last time, which is that we have this contrast between a d equals 1 random forest, no design situation where trees are being thrown down randomly, just to sort of get us back in the frame here. And there's really only this critical density where we have these power law size distributions of forest fires, and above it, everything explodes. Of course, it's a phase transition sort of story, but you get a giant component, and below it you don't have anything like that, and that's a real transition, a real change in stark contrast, I should say, to the hut model, where there isn't a critical threshold or critical density of trees. You can have lots of densities of trees that have power law size distributions of forest or subforests in this case. And it's a very structured thing. It doesn't, it's very low entropy. And if it's but if it withstands some attack or some assault from the environment, but if that gets characterized poorly, then, or changes, the environment changes, then you get into trouble. Okay, so we don't have to talk about this too much, but this is a bit of a funny, so in some ways this is terrible, right? Like, where is it? This is really a complementary cumulative distribution function, right? That's what we've framed as p greater than or equal to. Try to be very consistent with that. And then in here somewhere they have like a calligraphic p L greater than or equal to Li, so just no one cares. Anyway, that makes this a little hard to look at, and we don't even know, right, if this is log 10 or whatever. But this is looking at different things, and this is starting to look at some linear. So there are forest fires in here. These are forest fires. There's also things like packets on the web. So you can think of that as a one-dimensional piece that's being broken up in some way. Now, whether that's a robustness story, not sure. Okay, base, we're upset about that. Okay, so let's set up just the abstract calculation here, and you can work on this. It does use the Lagrange multiplier stuff. It's not as maybe out of control as that Mandelbrot one. But the idea is going to be this, that we're going to have some failure size, right? So this is our forest fire. This is now abstracting a little bit. There's some resource, which for us is, for the forest analogy, is going to be the fire breaks. And when we think about resource there, we think about the maintenance, or, there's creation of them, but then the maintenance of it, right? So there's time and money or whatever however you want to measure it, that goes into preserving these breaks, these fire breaks, and that there's some connection between them. And so we'll see why that makes sense. We want to minimize the forest fire sizes. That's the idea. And there's going to be some constraint on the resources, right? There's only so many fire breaks we can put in. And so the cost is going to be what's the probability of whatever it is that explodes times the size, or whatever that weight of explosion is. And we're going to go across all these sites. So that's the idea, right? And there's going to be some constraint. All right. So we'll just set this up. This is a bit funny how you can do this, I suppose. This is cost save of fire. And we're looking at all these sites on a grid. This is the probability that the ith site, and you'll do the simulation, gets a lightning strike, and then that's the area that's connected to it. Yeah. Right, it's part of some subforest or a forest that has some area. So every time it hits, it goes boom. And we're going to sum over all of them. So there's a little probability that's attached to every, so we've got some area. We're really essentially adding up all of the probability that lightning hits inside that area. That's going to come through there. There's a constraint. So how do we put in the constraint? And this is maybe where you'll see when we get to supply networks that there's a connection here. So we're going to sum again over all the sites. And the idea is that we've got some region, some area around it. Right, there's some subforest. It's got some fire break around it, and the fire break's length is going to be proportional to area to a half, and that's just a simple scaling thing. It's a dimensional analysis piece, right? So this is just saying, like, we have a square of area A, then a typical size, you know, the width of that square or the length of that square is length is 8.5. Or if the square is length squared, we will have length here. But since we're dealing with area, we're going to take the square root of it to get a sense of what a typical size of it, and that gives us an estimate of the circumference as well, at least proportional to. Now, every side in that area is going to contribute, so we're going to divide by the area of it to kind of get a normalization. So when we sum over the whole thing, we'll get the cost of the firewalls. So we're assuming isometry, that there's nothing funny in the shape, right? So that's the scaling here, that this is a nice scaling. And if we go up to d dimensions, or we go back to, say, 1 or 3 or 4, then this half is going to be replaced by the scaling. All right. So that's a question, and you can work through this, and you get, and it doesn't take too much work. You get the area, the probability of a forest fire of a certain area is going to scale as area to the minus gamma. So we get a parallel size distribution. Boom, boom. Exciting. Okay. But again, this is an optimality argument. This is different to what's happening over here, which is of course we're creating this thing, right? So this was this little greedy algorithm to kind of make something. I was going to say that it would be hard to go the other way, fill it up with, at least from this kind of toy model, fill it up with trees and then start to make fire breaks iteratively, right? Because your first one wouldn't do anything and then the next one wouldn't. It would be hard to find these breaks starting from, at least using this algorithm. I mean, we could see it, but using this kind of incremental algorithm of removing one tree at a time. There's a continuum version. I'll just sort of set this up. So there's a cost function. We're integrating over some space. There's some cost at each space. If gets hit. So we have some point in space. This is the probability, okay, that an Ewok jabs something, right, and it goes boom. Lots of systems explode. And so there's some constraint as well. So this is sort of, so this is in direct analogy to a couple of slides back, or the previous slide. There's some resource. Yeah. And then this, whether this is true or not, right? So you have to have, this is really the big thing that makes it work, that there is a relationship that's an inverse parallel between the resources and how much damage is done if that particular region is hit.